So the first clue that white dwarf stars could actually be violent came in the 19th century from this guy, John Russell Hind, who was actually son of a lace maker from the Midlands of England and working on the Naval Almanac. And he was surveying part of the constellation of Gemini when he saw a star that he was pretty sure hadn't been there when he'd last looked at it a little while ago. So it seemed to be a new star that had appeared. And it went away again. So maybe there's something exploded, something appeared, became very bright and went away. But then a few weeks later, another astronomer reported it was back again. If you plot brightness against time, here's some data from the amateur astronomers who monitor these things and do a fantastic job. What you can see is normally it's pretty faint, but it's still there. You can see it when it's not exploding. You've got a rather faint star, and every now and then it gets about 100 times brighter. So this is in magnitude scale, so it goes to a ninth magnitude from 14. That's 5 magnitudes, which is a factor of 100 in brightness.
So 100. So you could imagine if our sun got 100 times brighter, we would notice it here on Earth. That's a huge change. So that's a major event on these things.
Yeah, and so, but the puzzling thing is normally that sounds like an explosion, getting 100 times brighter. That sounds like something pretty cataclysmic. You imagine a bomb goes off, gets 100 times brighter. You wouldn't normally expect it to do it again. Normally bombs don't explode twice, the same bomb.
And this is doing it sort of every month or so, and it's doing it more than once. It happens and it keeps on doing this.
It's been doing it since the middle of the 19th century, every month or so. But there's no regular pattern. It's not as if it does it every second Tuesday or on every 40
so
days
like
or something.
It's the old faithful geyser that comes on every...
It's the old unfaithful geyser,
yes.
if you like. It does it whenever it feels like it. There doesn't seem to be a pattern to it, but it's roughly on monthly timescales.
So I always say that if you see something like this and you want to understand it better, what you really want to look at is the spectrum. Now remember, the spectrum tells us a lot more about the physical situation of what's going on.
Yes, so indeed, spectra were obtained of these things pretty soon. Now, if you remember what a spectrum is we take the light from the object. It just looks like a dot, it just looks like a star. We can't see any details. It's just far, far, far smaller than the smallest pixel of our best detector. But we can take the light from that pixel and put it through a prism or a diffraction grating and break it out into its component wavelengths. So down here we're plotting the wavelength in nanometers. This is from the ultraviolet out to the near infrared.
Yep.
So this is visible light. This is what the eye perceives as green. This is what the eye perceives as blue. This is what the eye perceives as red. And up here we're plotting the amount of power at each of these wavelengths. And this blue curve down here is what the spectrum of one of these objects looks like. There are actually many of these things. They became called dwarf novae. The first one, U Geminorum, was the one Hind discovered, but since then dozens more have been found. And you can see at most wavelengths it doesn't emit much light. But there are these big spikes. At this wavelength, 656.3 nanometers, and 486.1 nanometers, and other wavelengths down here, there's a huge amount of light.
And so those numbers ring a bell to Paul and me, and maybe even to you by now, because those are the places where hydrogen likes to emit light as it makes a transition from level 3 to level 2 in this case, level 4 to 2, 5 to 2, 6 to 2. So that's an interesting clue that these things, there's obviously hydrogen at play, and for some reason it's being up and making these transitions, so it's easy to identify.
And you've also got a bit of light in between these spikes, and this light, what we call the continuum, like the flat bit at the bottom, seems to increase as you go to short wavelengths, so it's very, very blue. Right. And that's a second clue. But much stranger indeed is what the spectrum looks like when it's at flare. So this is what it's like in between these explosions. When it's actually exploding, it looks quite different. What would you make of that, Brian?
Well, let's see. So it's still hydrogen. So we see the same transitions, but for some physical reason, instead of the material going from 3 to 2 in this case, it's going from 2 to 3 in this case. It's actually taking light from what would appear to be the continuum, and hydrogen sucking up light from the continuum, where here it seems to be emitting light from the continuum. So there's a physical process at play here, which will hopefully help us understand what's going on.
Okay, so in the next clip we'll talk about what can actually make spectra go up as opposed to go down.